What if I told you that December 15th won't bring any spectacular light show, yet it could still be one of the most important days for understanding the interstellar visitor 3I Atlas? Would you believe me? On that date, this traveler from another star system will be perfectly positioned in the sky for a task that doesn't make headlines, but one that ultimately defines its story, taking the most precise measurements of its trajectory yet. We aren't looking for dramatic flares or spins. We are hunting for thousandths of an arcsecond in its position, differences so minuscule that, when added up, reveal what the underlying physics is truly doing out there. By the way, I'd love to hear your thoughts on 3I Atlas. What's your take? Do you think it's a true alien craft or just another comet? Let me know in the comments below. And if you're finding this deep dive fascinating, please show your support by liking this video and subscribing to the channel. It helps immensely and lets me know you want more content like this. 3I Atlas is the third confirmed object to visit us from outside our solar system. Its hyperbolic orbit is the telltale signature that it isn't bound to the Sun and is merely passing through on a one-way journey. So far, its behavior fits what astronomers expect from an active comet. As it approaches the Sun, some of its ices sublimate, creating non-gravitational nudges, jets of gas and dust that can skew its trajectory away from a path dictated by gravity alone. Detecting these forces isn't about taking a pretty picture. It's about repeated astrometry, night after night, using telescopes in both hemispheres and performing careful data reductions. Why does the mid-December date matter? Because the viewing geometry improves significantly. A greater angular separation from the Sun, more usable nighttime hours, and an ideal temporal arc to compare data from before and after its closest approach to the Sun, perihelion. With this material, scientists can fine-tune the classic non-gravitational acceleration parameters. A1, A2, A3, check if the light curve suggests stable rotation or changes in activity, and recalculate the orbital solution with tighter uncertainties. If the corrections are small and consistent with normal outgassing, we'll have a sharper portrait of a typical interstellar comet. But if they are larger or directionally strange, we'll need to scrutinize the physical causes, jet orientation, nucleus morphology, thermal variations, before jumping to any extraordinary conclusions. None of this implies any danger to Earth at the predicted distance. The interest is purely scientific, refining how we model objects that did not form here. This fine-tuning is invaluable because it allows us to better estimate effective mass, porosity, and activity patterns without seeing the nucleus up close. In fact, for one-time visitors like 3I Atlas, precision is our only resource. Every tenth of an arcsecond gained today is knowledge we cannot recover tomorrow. The fundamental question is simple yet demanding. What minimal signal in the December 15th data would allow us to claim the trajectory changed more than expected from normal activity? To answer it, we must enter the engine room of high-precision astrometry, where a handful of pixels decide between noise and a solid clue. To know if 3I Atlas strayed even slightly from a purely gravitational path, looking isn't enough. We must measure it with almost surgical discipline. The key word is astrometry, converting points of light into sky positions with an accuracy that, from Earth, is like measuring the width of a coin from hundreds of kilometers away. This level of precision isn't magic, it's method. First, reference. Each image is anchored to a reliable coordinate system using dense and precise stellar catalogs, like those released by space missions dedicated to mapping the sky. Using these reference stars, software solves the plate solution, translates pixels to degrees, corrects for optical distortions, and defines the local map. Atlas's diffuse core is located via its centroid, the point where its light, spread across several pixels, is best balanced. Corrections are then made for atmospheric turbulence, for chromatic differential refraction, The atmosphere bends blue and red light differently. And for time, each exposure needs an exact timestamp to apply barycentric corrections, as Earth's motion around the Sun also shifts the apparent point. Then comes the art of cleaning the signal, stacking images to boost the signal-to-noise ratio without dragging the background, subtracting nearby stars, modeling the coma, that cloud of gas and dust which can skew the centroid, and, when possible, using filters that favor continuum light over gas emission lines. Even with all that, the raw data means nothing until we compare it to a prediction. This is where the famous OC residuals, observed minus computed, appear. If they are random, we're probably just seeing noise. If they show coherent patterns in direction and magnitude, something physical is pushing. Photometry runs in parallel. Measuring how brightness changes throughout the night helps identify rotation and outbursts. A peak in gas emission might coincide with a small positional shift, and that temporal coincidence is gold for distinguishing an instrumental error from a real jet. In coordinated campaigns, several observatories repeat the sequence. Same filter, same cadence, common protocols. The goal isn't a spectacular photo, but redundancy. If two teams thousands of kilometers apart see the same residual with different atmospheres and optics, confidence soars. On December 15th, this fine-tuned machinery is put to the test. The challenge isn't just to detect residuals, but to prove they persist when the time, phase angle, and instrumentation change. If they do, the next step is inevitable. Translating that tiny nudge into concrete physics, jet sizes, spin axis orientation, the thermal response of the material. But there's an awkward detail. Sometimes coherent residuals don't point where you'd expect from a typical active comet, and that's where models have to wrestle with the data. A persistent OC residual isn't a statistical fluke. It's the fingerprint of a small force acting over a long time. Translating that fingerprint into physics starts with a framework the community has used for decades for active comets, the non-gravitational terms. In plain language, these are coefficients A1, A2, and A3 that represent tiny thrusts along three directions of the orbital motion: radial, toward, away from the Sun; transverse, along the direction of travel; and normal, perpendicular to the orbital plane. They aren't magical buttons to make the orbit fit. They are a compact way of saying, this object behaves as if it had a tiny rocket oriented in a certain way. But where does this rocket come from? From the sublimation of volatiles erupting from active patches on the nucleus. When a region is illuminated by sunlight, it heats up and releases gas. This gas pushes in the opposite direction. The net effect depends on three things. How strong is the jet? How long does it stay on? And what is its orientation relative to the motion? If the object is also rotating, the effective thrust direction changes over time, and the model must include thermal lags, material doesn't respond instantly to light, and possible seasonal effects, hemispheres that are more active for months. In practice, teams don't guess A1, A3. They perform simultaneous adjustments of the orbit and non-gravitational parameters using thousands of measurements weighted by their uncertainties. Families of solutions are explored with Monte Carlo or Kalman filters to map the space of possibilities and their covariance. Sometimes a small change in A2 can mimic a slight adjustment in eccentricity. Other times, the normal term A3 is poorly determined if the observed arc doesn't yet cover a sufficient range of phase angles. That's why the December window is crucial. It lengthens the arc and disentangles correlations. There are more subtleties. The real thrust isn't constant. It follows a thermal law, increasing toward perihelion and decaying afterward, but not symmetrically. To capture this, if the material retains heat, GR functions are used to modulate A1, A3 based on solar distance and, in finer versions, on the illumination angle of active zones. When evidence of spin axis precession appears, models include the spin orientation and its evolution, because a slow change in the axis redistributes which zones are illuminated and when. And what would December tell us? If the residuals are well explained by a coherent non-gravitational pattern, for example, a significant A2 aligned with the direction of travel and stable over time, the message is that we're seeing a normal yet instructive interstellar comet. We learn about its activity level and possible active zone geometry. If, instead, the best solution requires an unusually large normal term, A3, or a phase shift that doesn't match the expected illumination, we must dig deeper into composition and thermophysics. Why? Because not all ices push the same way, and not all surfaces absorb and release heat identically. And that's where spectra start to speak. If a persistent residual forces you to choose between an incomplete model and real physics, the next compass is composition, because not all jets are the same. Which molecules are sublimating? At what temperature and rate? This decides both the intensity and the effective direction of the thrust. This is where spectra come in. Signatures of light that betray gases like CO2, H2O, CO, CN, and atomic metal traces. They aren't just chemical decorations. They are emission dynamics. Practically, an object with dominant CO2 production can start its activity farther from the sun than one dominated by water. This extends the temporal leverage of the transverse thrust, the famous A2 term, and can bias the orbit weeks in advance. Conversely, if water becomes the main driver only after perihelion, you expect a thrust pattern with thermal hysteresis, rising fast, falling slow, leaving a measurable mark on the residuals. To model this, the GR functions, which modulate A1, A3, adopt different curves depending on the dominant volatile and its sublimation energy. Thermal inertia and porosity complicate the story. Porous material stores heat and can continue releasing gas hours after sunset, displacing the thrust relative to the sun object line. If the nucleus is also covered in dusty crusts, the albedo, ability to reflect light, and conductivity change how deep heat waves penetrate. All this translates into lags that the model must account for, so it doesn't force A1, A3 to explain what is actually surface thermophysics. Spectra also help separate signal from geometry. At certain phase angles, sunlight scattered by dust can produce apparent tails or anti-tails that don't point where particle dynamics would suggest. Without chemical context and grain size information, it's easy to misread weird thrust where there's only optics and perspective. That's why coordinated campaigns mix spectroscopy with deep images. One tells you what's evaporating, the other how the dust carried by that gas is distributed. What would the community expect on December 15th? Correlations. That a temporary increase in CN or CO2 coincides with a slight coherent shift in the OC residuals. That the light curve shows a pattern compatible with active zones rotating in and out of illumination. That the dust-to-gas ratio explains why the centroid moves when the coma becomes asymmetric. If these pieces fit, the adjusted trajectory stops being a curve-fitting exercise and becomes a physical diagnosis. An uncomfortable question remains. What if the chemistry fits, but the residuals keep pointing in directions not aligned with the expected dominant illumination? When that happens, the focus shifts from what is sublimating to how is the nucleus oriented and spinning, and then rotation stops being a detail and becomes the main character. If chemistry tells you what can push and when, rotation decides where that push adds up at every instant. A spinning nucleus doesn't present the same face to the sun all the time. It activates and deactivates zones, attenuates and reinforces jets, and turns a continuous thrust into a modulated signal. So, when residuals persist but don't point exactly where average illumination dictates, the next question is, how is 3I Atlas spinning? Comets can rotate simply around a fixed axis, or in a complex state called tumbling, non-principal axis rotation, where the axis itself precesses or wobbles. In simple mode, the relationship between brightness, phase angle, and non-gravitational impulses is more predictable. The light curve shows clear periodicities, and the thrusts average to a stable direction. In tumbling, however, the orientation changes on two timescales, rotation and precession, and the effective thrust direction can drift over days, generating residuals that seem to migrate. How is this diagnosed from a distance? With high-cadence photometry and periodogram analysis, methods like Lomskargel, to hunt for periods in the brightness. If the light curve shows a repetitive pattern consistent over several nights and wavelengths, we have a good candidate for a rotation period. If multiple stable peaks appear or the period drifts smoothly, that points to precession or activity changes mimicking false periods. The key is coherence. Real periods survive when the phase angle and geometry change. Artifacts do not. Morphology helps. Deep images processed with gradient enhancement reveal jets and fans that rotate with the object. If a fan repeats its angular position with the deduced period, it confirms the diagnosis. If its angle shifts slowly night after night, precession is hinted at. Polarimetry, how brightness depends on the polarization angle of light, also contributes. Different grain types polarize light differently, and systematic changes can betray that illumination is alternately favoring zones with different dust. Why does this matter for December 15th? Because a well-resolved period and spin geometry allow us to predict when each active zone enters sunlight and to compare that prediction with the temporal evolution of the OC residuals. If peaks in orbital deviation coincide with the illumination windows of a specific zone, the model gains explanatory power. We don't just know there's thrust, we know which side it's coming from and when it hits hardest. Furthermore, the period and amplitude of the light curve infer something about the nucleus elongation. More elongated objects generate larger brightness modulations, and that shape impacts heat distribution. One final piece ties everything together. With rotation and activity characterized, thrusts translate into constraints on size, density, and porosity. How much mass is needed for those jets to produce exactly the observed residuals? Answering this isn't trivial, but it turns pixels and thousandths of a magnitude into kilometers and grams per cubic centimeter. And right there, where orbit meets mass, is where assumptions stop being enough. How do you estimate the true size from a distance without fooling yourself? We already know residuals can reveal thrusts, and that chemistry and rotation tell us when and where they push. Now for the most down-to-earth part, how big and heavy is 3I Atlas? At this distance, we don't see a defined disk. We see a point with a coma. So size isn't measured with a ruler, but with models combining brightness, albedo, dust, and gas production, and limits on non-gravitational acceleration. The first step is photometric. From the absolute brightness, the magnitude it would have at standard distances, and an appropriate phase function for comets, an effective illuminated area of the object is inferred. This number is converted to a diameter by assuming an albedo. What fraction of light does it reflect? Problem: comets typically have low and variable albedos, and the coma contaminates the nucleus measurement. So, radial brightness profiles and deconvolution techniques are used to separate as much as possible the nucleus from the envelope. In parallel, the physics of thrust offers another path. If you estimate a mass loss rate from spectral gas lines and the AFR parameter as a proxy for dust and assume a typical ejection velocity, you get a force. If astrometry gives an upper limit to the non-gravitational acceleration, Then force divided by acceleration gives you a minimum mass. It doesn't give the exact mass but a floor. For it not to move more than observed, it must weigh at least that much. This floor, combined with the photometric diameter, suggests an apparent density and porosity. Thermophysics adds more constraints. With thermal infrared, effective temperature and thermal inertia are estimated. Highly porous surfaces heat and cool differently from compact blocks. If the thermal brightness agrees with a dark, porous object, it reinforces low albedos and subunit densities, common in comets. If not, it forces a re-examination of dust grain size, crusts, and roughness. There are also rare but powerful shortcuts. A stellar occultation, when the object passes in front of a star, can outline a contour and give a direct diameter with kilometer precision. These events are brief and hard to predict, but if December offers favorable geometry, teams across Earth can try to catch the shadow with mobile telescope networks. A success like this shatters much of the uncertainty about shape and size at once. Even with all this, some degeneracies only yield with more simultaneous data: deep photometry, spectra, infrared, and astrometry on the same day. Exactly what December 15th promises. Because if on that day the limit on non-gravitational acceleration drops and the gas production rate rises, the mass floor increases, and if the effective diameter doesn't keep up, the implied density could fall outside the comfortable range. What would we do if the numbers point to a body that's too light or surprisingly dense for a comet? The answer isn't in a single curve, but in how the material is distributed around the nucleus, and that leads us to look at the dust with a different lens. When size, mass, and density numbers leave doubts, dust becomes a key witness. It's not just photogenic decoration. The tail and coma encode in their geometry the history of when and how material was released, and in their physics, the size and composition of the grains. If we understand this map, we can reconcile thrusts, albedos, and mass limits without inventing exotic properties. Let's start with two classic tools: syndenes and synchrones. Synchrones group particles released at the same time. Syndenes group particles with the same beta coefficient, the ratio of radiation pressure to solar gravity. Plotting them over a deep image of 3I Atlas reveals patterns. A fan following a recent synchrone suggests a punctual outburst. A jet matching syndenes of high beta indicates small grains easily expelled. This cartography, combined with the direction of motion and the Sun object-Earth angle, separates perspective effects from real dynamics. The AFAR parameter is the bridge to dust production. It roughly measures the effective cross-section of particles within a projected radius. Temporal series of AFAR taken with the same filter and aperture reveal trends: growth toward perihelion, plateaus, transient peaks. If an increase in AFAR coincides with a change in coma asymmetry, then the centroid's wobble isn't noise. It's dust displacing light and thus the measured position of the nucleus. Polarimetry refines the portrait. Sunlight scattered by grains of different sizes and structures polarizes in characteristic ways. A polarization peak at certain phase angles can betray porous aggregates versus compact grains. This matters for thermophysics. Porous aggregates retain heat differently, sustain weak jets for longer, and explain persistent tails even when gas production declines. Another clue comes from chromatic dependence. Comparing wide filters, e.g. R and I, with bands free of emissions helps separate the dust continuum from gas lines. If the tail strengthens in the continuum but not in the lines, the event was dust-dominated. If the opposite occurs, it was gas-dominated. This nuance decides how to interpret a notable A2, sustained gas thrust or photometric variations from dust moving the apparent centroid. Finally, morphology. Anti-tails that seem to point toward the Sun can emerge from projection effects when Earth crosses the dust orbital plane. Without modeling the geometry, A purely visual effect can be mistaken for thrusts in impossible directions. Again, syndines, synchrones, and phase angles are the antidote. If on December 15th we get deep images and polarimetry aligned in time with fine astrometry, the dust will tell us if the deduced thrusts make sense with the inventory of grains we see. But there's another spectrum that can tip the scales without touching a single grain: the thermal infrared, where heat, not reflected light, confesses the true nature of the visitor's surface. What happens when the thermal brightness contradicts the tale we thought we understood? Reflected light tells us how 3i Atlas looks. Thermal infrared tells us how hot it is and how it distributes that heat. When the two stories don't match, the culprit is usually the surface, its roughness, albedo, and conductivity. So, when the tail and coma suggest a certain grain inventory, but the thermal brightness numbers don't fit, the next step is to listen to the heat. In practice, two families of models are applied. The first, semi-empirical, like the Near-Earth Asteroid Thermal Model, NEATM, condenses the physics into a beaming parameter and a multiplier that captures how concentrated the thermal emission is toward the observer due to roughness, craters, and self-heating between the surface facets. If both are near 1, the surface behaves cleanly. If they are greater than 1, there is roughness or elevated thermal inertia that flattens the temperature curve. Adjusting this and the emissivity, the observed flux at various wavelengths converts to an effective diameter and albedo, independent of visible brightness. The second approach is thermophysical. It solves the heat equation on a mesh over an assumed shape, sphere, ellipsoid, or simple mesh, with parameters for thermal inertia, conductivity, heat capacity, and density. This simulates temperature maps that change with rotation and illumination angle. The beauty is that with a spin period already estimated from photometry, you can predict thermal curves throughout the night and see if the object cools as fast as it should. A very porous surface heats little and loses heat quickly. A compact surface stores and re-emits with a lag. This lag is measurable if you synchronize infrared with visible data. Why does this impact the trajectory? Because thermal inertia and roughness alter which zones release gas and when, subtly reorienting the non-gravitational thrusts. A hemisphere with insulating crusts can delay sublimation hours after peak illumination, displacing the thrust vector relative to the Sun object line. If the thermal model requires high inertia, but the tail indicates fine porous grains, there's a physical tension to resolve. Either the dust doesn't represent the dominant surface skin, or the thermal flux is contaminated by emission from dust in the coma. Spectral dependence enters here. Measuring in multiple thermal bands, e.g. around 8, 12, and 18 to 22 helps separate the surface from the coma. Fine dust has different spectral slopes. Observing at different phase angles also helps. If the thermal flux falls more slowly than the visible flux when the geometry changes, it's a sign of self-heating due to roughness. On December 15th, the challenge will be to synchronize astrometry, visible, and thermal data with sufficient cadence to see lags on the scale of minutes and hours. If the warm flux demands a larger diameter than inferred from reflected light, or vice versa, we will be facing two divergent paths with very different dynamical consequences. What do you do when thermal and photometric models demand different bodies? The only way out is to make them compete in real time under the same geometry, and that requires a campaign choreographed to the millimeter. Nothing we want to measure on December 15th happens by accident. Behind it is a choreography that turns observatories with different climates, optics, and latitudes into something like a single instrument spread across Earth. The premise is simple and strict. Same question, same protocols, and clocks aligned to the second. Without this, the orbital residuals, thermal curves, and photometry lose comparability and become mere anecdotes. The first piece is cadence design. In astrometry, regularity is more important than spectacularity. Sequences of short exposures separated by fixed intervals anchor a temporal arc that carries weight in the orbital fit. In photometry, continuous series of 1 or 2 hours per block are preferred, with an ABA pattern in filters to control atmospheric drifts. In the infrared, where the sky is fickle, dithering and chopnod pairs are used to subtract the thermal background without killing the signal. Next comes cross-calibration. Each site observes field standards, stars with known magnitudes, in the same filters near the object's path, to tie down photometric zero points and color terms. In astrometry, everyone adopts the same reference catalog and the same astronomical constants. Even the FITS headers follow an agreed format. Keywords for time, distortion, field rotation. The idea isn't bureaucracy. It's to prevent an hidden offset between catalogs from masquerading as a physical thrust. The third layer is error handling. Each team reports internal uncertainties, red noise, centroid scatter, seeing, and systematic ones, plate alignment, differential chromatic refraction. A central reduction group reprocesses subsets blindly to check consistency. If the same raw data processed by 2 pipelines gives compatible positions within 1S, the data escalates from useful to robust. If not, the discrepancy is tracked. An asymmetric coma? A bad flat field? Ignored partial saturation. The fourth element is the real-time link. A shared server receives preliminary stacks, light curves, and provisional OC residuals the same night. If one site detects a peak in CN or a change in AFR, the others immediately adjust their filter priority and cadence. If the IR suggests a thermal lag of tens of minutes, the visible series are densified to capture it. This ability to pivot is the difference between "we noticed something odd" and "we measured an effect." Finally, Plan B. Alternate windows in case weather knocks out a key node, and alerts for fleeting opportunities. A possible stellar occultation, an exceptional phase angle. A well-designed campaign assumes something will fail and still guarantees enough redundancy to answer the main questions. All this sets the stage, but no ballet is worth anything without performers who know their parts. What can each type of instrument contribute? Large mirrors with adaptive optics, medium wide-field telescopes, and space platforms. When the difference between rival hypotheses lies in thousandths of an arc-second and hundredths of a magnitude, a well-choreographed campaign only works if each instrument plays its note in its register. An 8 to 10 meter giant with adaptive optics, AO, is not the same as a medium wide-field telescope or an orbital observatory. To squeeze the most out of December 15th, we must understand what each one measures best and how to assemble those pieces seamlessly. Large telescopes with AO are the image surgeons. They correct seeing, cut through the coma, and resolve fine morphologies near the nucleus. They won't see the nucleus as a perfect disk, we're too far, but they can isolate jets, fans, and subtle asymmetries that bias the centroid. This information is gold for correcting astrometry and for synchronizing with high-cadence photometry. If a jet turns on at a certain angle, we expect a directional thrust and a corresponding blip in the residuals in the same interval. Medium and wide-field telescopes are the marathon runners. Their job is to sustain cadence and coverage. Long astrometric arcs with homogeneous uncertainties, continuous light curves, and stable filter series to track AFR, dust, and separate gas lines. They are also the first line for alerts. If they detect an abrupt brightness increase or tail changes, they can trigger adjustments in AO and infrared priority. Their large field also allows them to hunt for stellar occultations that give direct size limits if the geometry allows. In space, the strengths change. A telescope like Hubble excels in stable angular resolution without atmosphere, ideal for coma and fine tail morphology and for astrometry with very controlled systematics. Space-based infrared avoids the terrestrial thermal sky and measures warm flux with a sensitivity impossible from the ground, nailing effective temperatures and thermal inertia with less background ambiguity. The common space denominator is stability. When you need to distinguish a lag of minutes between thermal and visible peaks, space removes most of the atmospheric noise. There are, however, clear limits. Planetary radar, so powerful for nearby asteroids, doesn't reach here. The distance and apparent size of 3I Atlas make useful echoes unfeasible. And in continuum radio, except for specific SETI campaigns, the dynamical priority is in optical, IR, and radio lines. So the trick isn't to point everything at everything, but to assign questions to AO, jet geometry, to medium telescopes, high-cadence astrometry and AFR, to space, thermophysics, and seeing-free astrometry. The glue is shared time. If AO sees a fan rotating, the medium telescope must record the photometric change, and space must measure the thermal lag, all during the same object rotation. When this trio aligns, models stop being aesthetic choices and become diagnostics. One last piece is missing for the puzzle to close. How are models compared and decided upon when several explain the data more or less? The answer isn't in the telescope, but in how we weigh the evidence. When two models explain more or less what we see, instinct wants to choose the one that fits best. Science, instead, demands measuring how much better and at what cost. With 3I Atlas, distinguishing between normal cometary thrust and unusual dynamics isn't resolved by eye. It's resolved with model comparison and out-of-sample prediction. The golden rule is simple. The best model isn't the one that fits the most, but the one that predicts best without inflating parameters. First, the toolbox. For orbits with non-gravitational terms, families of solutions differing in structure are fitted, from the minimal, gravity only, to variants with A1-A3 modulated by thermal GR functions, and even schemes incorporating rotation and lags. Each family is calibrated with the same OC set. They are evaluated with criteria like AIC or BIC, which penalize the number of parameters. If you add complexity and the fit barely improves, the criterion charges for that luxury. In parallel, residuals aren't judged just by size, but by pattern. Streaks in one direction, periodic wiggles, changes when crossing a certain phase angle. Noise is messy. Physics leaves coherent fingerprints. Second, priors. Bayesian approaches allow incorporating what we already know about comets. Possible ranges for A1-A3, typical thermal inertia of porous surfaces, ejection velocities. Reasonable light curve amplitudes for elongated bodies. This isn't about forcing an answer, but about preventing the math from choosing physically absurd solutions, e.g., thrusts requiring impossible gas rates. The result is posteriors, distributions of parameters reflecting both data and prior knowledge. Third, out-of-sample prediction. Here, December is both judge and participant. Models are fitted with prior data, and the solution is frozen to predict positions and brightness for the December 15th window. Then it's compared with what's observed without recalibration. If a simple model nails the positions within uncertainties and reproduces the evolution of AFR and the thermal lag, it scores points. If a complex model needed 10 knobs to explain the past and still slips in prediction, it was overfitting. It explained the noise, not the signal. Fourth, sensitivity tests. Small changes in calibrations, reference catalog, chromatic correction, plate scale shouldn't flip the verdict. If a result depends on a fine technical decision, it's reported as fragile and independent evidence is sought. Another station, another technique, another filter. The goal isn't to be right, but to resist honest attempts to refute the conclusion. Finally, the threshold for affirmation. The community doesn't declare unusual dynamics for a nice-looking residual. It looks for convergence. astrometry favoring the same thrust vector, photometry synchronizing peaks with expected illumination, thermal data fitting the required inertia. Only when three lines tell the same story does the label change from possible to probable. One test remains that few can see and that can break ties in seconds, a fleeting, punctual, and fiercely objective phenomenon that turns uncertainty into silhouette. If it appears, no gentle parameter will disguise it. We will be ready to read its shadow when it crosses the path of a star. There is one experiment that, if successful, cuts through discussions like a scalpel: the stellar occultation. When 3I Atlas passes exactly in front of a star, its silhouette projects a shadow onto Earth. If you place telescopes along that path and measure when the light blinks out and returns, you turn a fuzzy point with a coma into a contour with kilometer precision. It's not interpretation. It's geometry with a clock. The challenge begins weeks before with refined ephemerides. The shadow path is calculated. A ribbon tends to hundreds of kilometers wide, crossing continents or oceans, and a mobile network is assembled. Small telescopes, sensitive cameras, and time synchronization via GPS. Each station provides a chord, a segment of the contour. Depending on where it crossed the shadow, several parallel chords reconstruct the profile. Diameter, elongation, even hints of contact binaries if notches or breaks appear in the light. The coma is the enemy. To minimize its trickery, cameras work with short exposures, 10-50 microns, moderate apertures, and, when the star allows, filters favoring continuum over gas lines. Additionally, the background is modeled and subtracted immediately before and after the event. Thus, the star's abrupt dimming isn't confused with the coma's smooth variations. In bright occultations, a subtle phenomenon can appear at the center, the central flash, an enhancement from diffraction and refraction in the dust atmosphere very close to the nucleus. If detected, it offers an extra meter of detail about the fine structure around the body. Timing is everything. Records are stamped to the millisecond with verified GPS or NTP. An error of 0.01s translates to hundreds of meters at typical relative velocities. With these times and the predicted apparent trajectory, each observer delivers two hard numbers: disappearance instant and reappearance instant. Added together, they give a local width of the silhouette. Compared between sites, they draw the contour. If a station doesn't see the occultation, a non-detection also informs. That null result cuts the solution space and prevents oversizing the body. Why does this test weigh so heavily for December 15th? Because a direct geometric diameter breaks degeneracies, fixes the effective area without albedo assumptions, anchors thermal models, and, combined with non-gravitational acceleration limits, raises a mass floor with fewer ifs. If the silhouette shows strong elongation, it explains photometric modulations. If it reveals companions or fragments, it rewrites jet dynamics and thrust distribution. But there's a final trap. The shadow might fall over an ocean or regions without coverage, and the best prediction remains a gamble with a margin of error. What do we do if the path shifts kilometers at the last minute? Then the strategy must change from the accuracy of a scalpel to the resilience of a network. Planning a stellar occultation is betting on a thin line that can move kilometers in the final hour. If the shadow escapes over sea or clouds, there's no scalpel. We must operate with a multi-tool approach. The keyword is intelligent redundancy. Not repeating the same thing, but covering different failure modes with data that complement each other and together answer the same question. First, size without a shadow. When the occultation fails, the hard backup is thermo-infrared synchronized with visible photometry. Fitting a thermophysical model with 2 or 3 thermal bands and a well-sampled light curve reduces the degeneracy between diameter and albedo. If the warm flux demands a certain emitting area and the photometric modulation is small, the body can't be extremely elongated. If the modulation is large but the thermal signal is low, the albedo must be higher or the thermal inertia lower. It's not a silhouette but a numerical fence that narrows the solution range. Second, the nucleus in the fog. With adaptive optics or very fine seeing, the coma is modeled, and an effective point-like nucleus is extracted via controlled deconvolution with a well-characterized PSF, guide stars in the field. We don't see the nucleus, but we constrain how much it can contribute to the central light without violating the PSF shape. This limit, used as a prior in the thermal fit, sets plausible minimum and maximum for the invisible diameter. Third, dust as a witness. The syndines, synchrones, and polarimetry taken the same day determine the typical grain size and dust-to-gas ratio. With that, the AFR parameter becomes a scale. Too much diffuse light near the nucleus implies more fine dust and, thus, greater bias. This bias lowers the OC and prevents an asymmetric coma from masquerading as orbital thrust. It's a defense against false positives of exotic dynamics. Fourth, resilient astrometry. When weather breaks the ideal cadence, staggered windows between hemispheres are used to weave a continuous arc. Positions are adjusted with homogeneous catalogs and calibrated times. If one site fails, another takes over. The secret is in the weighting. Not all measurements are equal. Each series is rescaled by its internal dispersion, and jackknife tests are run. Remove one block and see if the orbital result changes. If it doesn't, the fit is robust. If you locate the weak link, you correct it. Fifth, light prediction verification. With the model frozen the previous night, ephemerides and expected residuals for the next session are generated. The team on duty observes, uploads raw data, and the central group compares hot. Do the new positions fall where they should? If not, an alert is issued, and filters, cadence, and AO are reprioritized. This real-time feedback separates narrative from evidence. All this prepares the ground for an inevitable step: fusing thermal, visible, astrometry, and chemistry into a single solution that says what is pushing, how much, and in what direction. Doing it well isn't averaging. It's assimilating data with memory and context so the model learns from every clue without being fooled by any. How is that mathematical choreography achieved without breaking the physics along the way? Combining astrometry, photometry, spectra, and thermal data isn't stacking files. It's assimilation. The idea is clear and demanding. A single physical model that, with one set of parameters, reproduces positions, brightness, lines, and thermal fluxes within their errors. If to explain the positions you have to break the thermal fit, or vice versa, it's not reality that's failing. It's your model. The path begins with a forward model. A base shape, sphere or simple ellipsoid, its period and spin axis, a minimal map of active zones. The thermal law modulating sublimation with solar distance, and the grain distribution responsible for the near-nucleus dust are defined. This engine generates, for any date, 3 predictions. 1. A non-gravitational thrust vector, magnitude and direction, that feeds the orbital integrator. 2. An expected light curve and AFER from the orientation of active zones and dust. 3. A thermal flux per band dictated by inertia, albedo, and roughness. No free parameters that only serve one subset of data. Every knob affects everything. To fit, the community often opts for 2 families of techniques. One is MCMC, Markov Chain Monte Carlo, which explores the parameter space with physical priors, realistic ranges of thermal inertia, ejection velocities, Comet albedos, and returns posteriors, which combinations fit all the data at once. The other is a Kalman filter. When data arrives in real time, The model predicts the new measurements, corrects, and the covariances are updated consistently. In both cases, the crucial part is propagating uncertainties to the ephemeris. It's not enough to fit nicely. You must know how sure you are about where the next point should fall. The statistical glue is comparable metrics: total log likelihood, sum of likelihoods per channel, BIC, ACIC to penalize complexity, and, above all, out-of-sample prediction. Models frozen with prior data that bet on December 15th without touching knobs. Then they are contrasted against what's observed. If the model that best explained the past slips in December, you learn that you missed some physics. If it's correct within 1 or 2s in all channels, the confidence level rises. Subtleties make the difference. Bayesian hierarchies allow different observatories to have their own photometric zero points and noise without contaminating the comet's physical parameters. A centroid bias term from the coma can live as a nuisance parameter that the model learns and subtracts. And posterior predictive checks avoid Pyrrhic victories. New data is simulated from the posteriors and its statistics are compared with the real set. If they don't resemble each other, the fit was a mirage. And the decisive signal, a thrust vector whose direction and magnitude remain coherent with rotation and illumination over several nights. And that also closes with AFIR and thermal data without demanding physically absurd gas rates or temperatures. That elevates the explanation to normal, but well resolved. Cometary dynamics. If, instead, the assimilation insists on a large normal term not sustained by the chemistry or spin pattern, the anomaly stops being a rumor and becomes a legitimate question. December 15th is, by design, a cross-examination. The adjusted orbit must agree with the dust we see and the heat we feel. If those witnesses refuse to testify, we'll have to interrogate the next one at a wavelength where the comet cannot lie. If reflected light and heat can confuse us with dust and roughness, there's a window where 3i Atlas has no possible makeup. The spectral lines in the radio and submillimeter. There, we don't see how it shines. We see molecules moving. Each line, CO, HCN, CN, H2O via proxies, is shifted and broadened by the Doppler effect. That shift and width are a polygraph. They reveal expansion velocities, temperatures, and, when mapped, flow directions. With this, the non-gravitational thrust stops being an abstract term, A1, A3, and becomes a linear momentum we can count. The logic is direct. If you know the production rate, Q, of a molecular species and its exit velocity, V, xp, you can estimate the mass flow rate the jet injects and, therefore, the net force. While Q suffers from dust and geometry issues, in radio the rotational lines respond to local density and temperature, and their profile, peaks, asymmetries, wings, betrays whether the gas is leaving isotropically or is collimated. Asymmetric, broad profile suggests nearly spherical expansion. A profile with a shoulder or double peak suggests directed jets that, when integrated, do move the orbit. Velocity maps, 3D cubes, 2 angular coordinates plus Doppler velocity, are the ace up the sleeve. With interferometers like ALMA, which resolve comas across tens of thousands of kilometers, blue lobes, gas coming toward us, can be distinguished from red lobes, gas moving away, and the jet cone can be reconstructed. If that axis coincides with the rotation phase and with the night's OC residuals, then all the thrust measured in the sky, astrometry, points to where the gas is actually leaving, radio. And if it doesn't coincide, the model must explain why. Thermal lags, axis precession, or a second jet hidden in visible light. There are decisive bonuses. First, isotopic ratios place 3i Atlas in the context of domestic comets versus typical interstellar material. They don't change the orbit, but they anchor where those volatile properties might come from. Second, the temporal evolution of Q measured night by night, rising, stabilizing, falling, feeds directly into the GR function modulating A1, A3. We no longer choose it by habit. The gas extracts it. On December 15th, a radio series well synchronized with visible and infrared can close the momentum balance. What the gas declares it's pushing must be consistent with what the orbit accepts was pushed. If thrust is missing, our mass limit rises. If there's excess, we are overestimating Q or V exp, or misreading dust as gas. And if the velocity maps show a stable jet outside the expected plane, the puzzle rotates. It's no longer just how much it pushes, but from what geometry it's born. To answer that, we must reconstruct the complete 3D orientation of the spin and the jet. Not in the sky plane, but in 3D. How is an axis we cannot see tilted? And what clues do its shadows leave in the light curves and Doppler peaks? Knowing where the jet is pointing in space isn't an aesthetic luxury. It's the hinge between what the gas declares and what the orbit accepts. The challenge is to reconstruct the 3D geometry of the spin axis and jet with clues we see projected onto the sky plane. To do this, 3 clocks must be combined: the rotation phase, light curves, the angular position of features in the coma, jets seen with high resolution, and the blue-red imbalance in the gas Doppler peaks. The first step is to locate the rotation pole. With the estimated light curve, a synodic period, which we measure from Earth and isn't always the true sidereal period because the geometry changes as the object moves. That phase shift is corrected by testing candidate poles on a celestial sphere. For each pole, we simulate how the illumination of the supposed active zones would have varied, and if that reproduces the observed modulation. If we also have images with AO or from space showing a fan repeating its position angle with a consistent period, that angle constrains the great circle where the pole lives. Second, the precession cone. If the light suggests tumbling, 2 periods, smooth changes in amplitude, or if a jet slides slowly from night to night, the axis isn't fixed. It describes a cone. It's parameterized with an opening angle and precession frequency. Projected onto our line of sight, it must produce the same drift of angles we see in the jets and the same breathing in the light curve. Models that survive both tests stay on the table. Third, the jet vector. The Doppler profile of a volatile line, e.g. CO, shows if, during the considered rotation, the gas leaves preferentially toward us, stronger blue peak, or away, red peak. By sweeping through several phases, the latitude and longitude of the active source on the body can be inverted. When the source crosses the apparent meridian, the profile symmetrizes. When it emerges into the near hemisphere, blue dominates. When moving away, red dominates. This pattern crossed with the deduced rotation fixes the jet's 3D orientation within the pole's frame. The fourth gear is torque. With the jet located, we can estimate the moment it imparts on the body proportional to Rxf, and thus foresee subtle changes in the period. And if the jet doesn't pass through the axis, a growing or decaying precession. If December brings sufficient cadence, that period drift, small but measurable, serves as an independent auditor. It confirms that the jet we see is the one turning the dynamics. A famous ambiguity remains. Many poles have mirror solutions, 2 orientations that project nearly the same. To break it, observations separated by very different geometries are needed, and if possible, a critical photometric event when the active source abruptly enters or exits sunlight. If the prediction nails that change to the minute and degree, the 3D map stops being a nice drawing and becomes a dynamical lever. What does that lever reveal when we apply it to the complete history of thrusts and residuals before and after December 15th? With the axis and jet placed in 3D, we can finally open 3i Atlas's ledger. We can sum up night by night the impulse the gas imparts and translate it into a cumulative dV. We're We're not talking about a dramatic rocket. We're talking about millimeters per second integrated over weeks. But in orbital dynamics, millimeters per second today are arc seconds of difference tomorrow. And that is exactly the kind of deviation that December 15th can exhibit or rule out with authority. The ground-level procedure is accounting. From each spectral session, we get a production rate, qt, and an expansion velocity, v, xpt. The jet's 3D orientation gives us the thrust vector. We multiply by the time interval dt and divide by the minimum admissible mass, the one required so that the non-gravitational acceleration doesn't break the prior OC residuals and accumulate. The v for s qt emitted mol v xpt sid mem. Then, this impulse budget generates a trajectory slightly different from the purely gravitational one, with a covariance that grows as we move away from the last astrometric anchor. December 15th acts as a settlement date for 3 reasons. First, it lengthens the post-perihelion arc enough for the non-gravitational terms to stop mimicking eccentricity or argument of perihelion adjustments. Second, it offers clean geometry, better separation from the Sun, more tracking hours, and varied instrumental dispersion, ideal for detecting a coherent drift in the residuals. Third, it allows honest out-of-sample prediction. You take everything prior, freeze the model, and see if it nails that night's positions without touching a single knob. What would the community consider a significant signal? Not a single point, but a pattern. Coherent residuals. Constant direction over several hours, on the order of tenths of an arc-second. Repeating at independent stations and reversing or modulating with the expected phase of the dominant active source. If, in addition, the light curve shows the same rhythm and the infrared its corresponding thermal lag, the causal chain is closed. Chemistry, thrust, dV, astrometry. And if the accounting doesn't balance, there are 2 routes. Either the impulse budget is short, lacking gas or underestimating VEx, and then the mass limit must be lower, or it's long, excess thrust according to the gas, and then either we are overestimating Q due to dust contamination, or the thrust isn't born where we think. In this last scenario, a difficult suspect appears, a normal term outside the plane not explained by the deduced illumination or precession. The December 15th settlement, if it exhibits precisely that out-of-plane thrust, will force us to answer an uncomfortable but fertile question. Is the surface geometry, reliefs, caves, crusts deflecting the jet? Or are we seeing multiple sources turning on and off like a system of natural valves out of phase with each other? An out-of-plane thrust isn't automatically a mystery. Often, it's topography on a small body, full of holes, slopes, and protrusions. Light doesn't heat evenly. Shadows lasting hours, walls concentrating radiation by multiple reflections, cavities trapping gas until pressure surpasses a threshold. And boom, an episodic jet that doesn't point where average illumination dictates. If you add rotation and precession to this geography, the thrust vectors can tilt and dance far from the orbital plane without violating any exotic physics. Think of multiple active sources. It's not rare for a nucleus to have patches with exposed volatiles and others covered by more refractory crusts. Each patch has its latitude, longitude, relief, and thermal history. At local dawn, a sun-facing wall receives grazing light and heats up suddenly. It releases gas with a well-defined direction, normal to the wall, and for a few minutes its thrust dominates. Hours later, the sun enters a depression. Gas accumulates, pressure rises, and escapes through the cave's neck with a collimation that doesn't match the radiant vector. If you integrate all these little kicks over one rotation, the vector average can tilt out of the plane. Modeling this requires moving from smooth A1-A3 to a scheme with n sources. For each one, a simple thermal law, on-off with a threshold, lag from inertia, A local orientation, normal to the facet, and a weight, relative production rate, are defined. The engine generates, per rotation phase, the thrust vector and averages it over the scale that astrometry resolves, minutes to hours. With 3 or 4 well-placed sources, it's possible to reproduce persistent residuals and also the light curve modulation. The trick isn't to fit for fitting's sake. Each source must be tied to real features in the coma, jets seen by AO or space, and to Doppler clues betraying its hemisphere, blue-red. Seasonality complicates and helps. With a certain obliquity, one hemisphere can be better illuminated for weeks. The same sources yield more over time and change their efficiency as they lose surface volatiles. Thermal fatigue then appears. Cracks opening new conduits, landslides exposing fresh ice, and, occasionally, micro outbursts of dust. These episodes, if documented with AFR series and spectra, explain punctual residuals without rewriting the global dynamics. How far can we trust a multi-jet model? The answer lies in cross-consistency. If the activation phases the model requires coincide with changes in CO2 to CN lines, with twists in jet morphology, and with photometry peaks, we're on the right track. If, to explain a large A3, the model demands sources in locations incompatible with what AO or velocity maps show, we must admit it. Topography is no longer enough. And there the next natural dilemma appears, equally demanding. When topography doesn't explain the out-of-plane kicks, the alternative isn't a metaphor. It's body mechanics. Is it still a single block? Or are we seeing fine fragmentation that changes the mass distribution and thrusts mid-flight? When topography is no longer enough to explain out-of-plane thrusts, the next suspicion is uncomfortable, but common in comets. Fine fragmentation. The nucleus doesn't need to split into 2 visible pieces. Flakes, decimeter-sized blocks, or a cloud of co-orbital clasts are enough to change the dynamics. Each active fragment adds its own jet, its own dust shadow, and its own contribution to the residuals. The result, seen from afar, can look like a weird thrust when it's really the vector sum of many little pushes not born from the same point. How do you recognize a nucleus that isn't a single one? In a deep image, the first hint is secondary condensations aligned with the trajectory. Slightly more extended than a star, but more compact than the coma. With AO, or from space, these beads can separate tens to hundreds of kilometers from the main nucleus. If they exist, the measured centroid can jump depending on which component dominates in each exposure, biasing the astrometry if not modeled. Hence the importance of a well-characterized PSF and visual inspection of residuals. A point cloud with 2 families is a shout of fragments. Photometry offers another clue. Brief flares, new asymmetries in the light curve, or changes in amplitude that don't follow the usual rotation pattern. A fragment that activates or deactivates, or that rotates with a different period. Injects variability that doesn't fit a single surface rotating in and out of light. In parallel, syndines and synchrones reveal multiple tails with different temporal origins. If, to explain the dust geometry, you need more than one recent synchrone, there are discrete episodes of material release, compatible with breakups. In the thermal infrared, a population of fragments can inflate the warm flux of the coma at small distances from the nucleus, making a naive fit demand a larger diameter than it should. Separating the surface from hot dust is crucial. Without that separation, a strange density might just be dust emitted by multiple nearby sources. And in sub-mm radio, Doppler profiles with persistent shoulders or multi-peaks, changing phase as if they were out-of-phase jets, can denounce several emitters moving in tandem. The physics behind this requires no exoticism. Outgassing torques can accelerate the rotation, spin-up, until it nears a critical period where low-cohesion materials, forces on the order of pascals, fail and detach. Small losses don't destroy the nucleus. but they reconfigure its mass distribution and, with it, the response to subsequent jets. If precession also changes with time, it's a sign that the moment of inertia tensor is no longer the same. What changes on December 15th if there is fine fragmentation? That the out-of-sample prediction becomes the test of fire. A single-body model should systematically slip, while one with multiple components would explain the drift and the new photometry without tricks. And if AO or space capture co-orbital condensations, the verdict will be hard to ignore. The most tense step remains. If the nucleus is losing pieces and the period is moving, we must calculate how close it is to the stability limit, because one more small change could decide between weeks of quiet activity or a major reconfiguration that rewrites the apparent trajectory in a matter of days. If 3I Atlas is losing pieces, the uncomfortable question is immediate. How close is it to the spin limit its body can withstand? In fragile objects, the rotation metronome marks the destiny. A comet isn't a granite block. It's usually a rubble pile of low cohesion with ice, dust, and voids. In that regime, the critical period, PC, below which centrifugal force surpasses self-gravity and the feeble cohesion, can be approximated to first order. For typical cometary densities, 0.3, 0.6 g, CE3, the threshold falls to hours, not minutes. But cohesion isn't zero. Small forces of pascals stretch that limit until they don't. The problem is that outgassing torques don't stay quiet. A persistent jet not passing through the axis imparts a torque that changes the angular momentum and the rotational energy. If the moment of inertia is reduced by mass loss or internal reconfiguration, it's a vicious circle. More spin, more stress, more detachments, lower I, and easier acceleration. Detecting this from a distance depends on high-cadence photometry. If the period measured 2 weeks ago isn't exactly the same, and the light curve amplitude changes, the metronome is moving. December offers a unique audit due to the coincidence of techniques. Astrometry showing residuals with synodic modulation synchronized with a light curve whose period drops by milliseconds per hour, and with jet morphology displacing angle by angle suggests real torques, not artifacts. If, in addition, the thermal infrared indicates low inertia, fluffy skin, the spin-up scenario becomes credible. Surfaces poor in cohesion respond faster to light and jets. Now, the limit isn't just a number. Shape matters. An elongated body concentrates stress on necks or lobes. A contact binary is prone to opening cracks at the junction. Signals to watch for. Appearance of new harmonics in the photometry. Hint of changed shape. Brief flares coincident at several sites. Dust micro-outbursts. And discrete steps in the period after an activity episode. In deep images, new plumes that didn't exist the previous week are traces of fresh cracks exposing ice. What does this not imply? It does not imply danger to Earth. At the predicted distance, any reconfiguration is a local event. What it does imply is dynamical uncertainty. A change in mass distribution and active source orientation moves the fine prediction of the orbit via non-gravitational terms. That's why on December 15th we don't just measure positions. We measure the tempo of the metronome. If it confirms acceleration and fatigue, the post-December forecast must incorporate a torque model that doesn't assume constancy. And there the next challenge looms. With the metronome altered, how reliable are the ephemerides beyond December? And what role will distant encounters with planets play in amplifying or damping that fate? With the rotational metronome under suspicion, the practical question is brutally simple. How far can we trust the ephemerides after December 15th? For active one-time visitors, predicting isn't drawing a line. It's propagating a cloud. The orbit adjusted that day isn't a point. It's an uncertainty ellipse in velocity space that, as time advances, stretches, rotates, and can diverge if even a hint of unmodeled thrust remains. The standard tool to avoid self-deception is creating clones, hundreds or thousands of neighbor solutions to the best orbit, sampled according to the Fitts covariance matrix. Each clone is integrated into the future with the same dynamical model: solar and planetary gravity, radiation pressure, irrelevant for the nucleus, and non-gravitational terms with the validated thermal GR function. The result isn't a unique line but a fan, a volume of probable trajectories. If the non-gravitational model is well calibrated, the fan stays compact. If it's biased, e.g., because the real activity decays slower than assumed, the cloud opens up and predictions become fragile. Here, distant encounters enter. At the predicted distances, Earth doesn't play a role, but the gas giants, particularly Jupiter, can sculpt 3I Atlas's exit with small deflections that, added over decades, mark the difference between above or below the ecliptic plane in the far future. We're not talking about dramatic detours. We're talking about perturbations that change the asymptotic direction of the hyperbolic orbit slightly. To diagnose them, the community uses analysis in the B-plane, the target of the fictitious encounter with the Sun. There, the dV near perihelion equates to moving the impact point on the target and rotating the exit vector's direction. That's why the December 15th astrometry is so valuable. It anchors that B-plane with small error bars and allows calculating deflection angles with uncertainties that fit on a slide, not in a paragraph. Mathematically, the change in oscillating elements from a brief thrust integrates over time. Near perihelion, the transverse direction is favored. An honest A2, sustained for a few hours each day over several rotations, can leave a signature that astrometry detects as a coherent A-track. The total energy changes little, but the hyperbola's orientation does. What does this translate to physically? The asymptotic exit vector. Its direction is 3I Atlas's final aim as it leaves the solar system. If we can nail that vector with precision, we can backtrack the trajectory for studies of probable origin, though with limits from interstellar travel times, and above all, predict future observability for facilities that want to pursue the object when it's farther away. Orbital arithmetic also sets sane expectations. A modest dV doesn't turn a hyperbola into an ellipse. It doesn't capture the object. It doesn't change the story in terms of it stays. It changes what we can say with numbers about its exit. And there appears the practical consequence. If we reorient that vector well, we can decide where and when to squeeze the last useful measurements before the visitor becomes unreachable. But to squeeze that final window, we must negotiate with an old enemy of any precision measurement, Earth's atmosphere, and squeeze it to our advantage. It can be done if we know how. The atmosphere is both enemy and ally. It distorts wavefronts, blurs the coma, and twists hundredths of an arcsecond with thermal caprice. But if we understand and use it to our advantage, it grants resolution, stability, and more honest uncertainty metrics. December 15th isn't about defeating the air. It's about taming it. First, seeing isn't a number. It's a temporal spectrum. A site with 0.8 on average can have spells of 0.5 that are gold for fine astrometry. So, it's better to segment the night. Instead of one long stack, microseries, packets of 5 to 10 to be endured, are built and labeled with the instant FWHM of guide stars and the tip-tilt frequency. Then, when adjusting positions, each block is weighted by its real quality, not accumulated minutes. This natural selection reduces the tail of errors that usually inflate OC residuals. Second, adaptive optics, AO, isn't just for pretty pictures. With a laser or a bright nearby star, AO not only reduces the PSF size but, crucially, stabilizes its shape. A well-characterized PSF allows more reliable deconvolutions and better centering of the effective point-like nucleus under the coma. If the field lacks a natural guide, a laser AO with careful calibration of the cone focus with the sky can save the night for jet morphology and robust centroiding. Third, differential chromatic refraction. At low altitude, the atmosphere refracts blue more than red. The apparent center shifts with color and altitude. Solution: observe in filter pairs, e.g., R and I, and model the DCR with field stars of known color, or work in a narrow red filter to minimize it. Reporting positions with and without DCR correction helps detect biases. Fourth, lucky imaging and speckle. On medium telescopes, thousands of short exposures, 10 to 30 mean seers, and selection of the best percentile reconstruct a sharper nucleus. Even though 3I Atlas remains unresolved, a centroid measured in still images weighs more than one in a turbulent sea. Fifth, extinction and background. Atmospheric dust, aerosols, inflates and contaminates AFAR. Measuring standards at the start, middle, and end of the night and recording PWV, precipitable water vapor, with local monitors allows correction of color and photometric 0 point. In thermal infrared, well-designed chopnod patterns and wide dithers are the difference between a useful flux and a carpet of noise. Sixth, dome wind and collimation. Small thermal gradients in the dome create internal seeing. Opening vents, equalizing temperatures, and verifying collimation when changing altitude reduce offsets that disguise themselves as coma asymmetry. Lastly, predictive meteorology. Local mesoscale models, WRF, offer windows of stable boundary layers. Scheduling astrometric blocks in those windows and leaving heavy photometry for the rest maximizes the return. With the air tamed, the limit is no longer the atmosphere, but the object's physics. And with that ceiling moving upward, we can face the dilemma that arises when everything fits except one detail that won't let go. A small but persistent normal thrust that survives AO, DCR, and chromatisms. If it's not air, nor dust, nor sufficient topography, what natural mechanism remains on the table to explain such a stubborn out of plane without crossing the line into the extraordinary? If we've already tamed the atmosphere, purified dust and topography, and a small but stubborn normal term A3 still remains, the question is, what mechanisms can sustain it without crossing into the extraordinary? A list exists and doesn't require inventing new physics. Oblique nozzles and nozzle effect in cavities. A jet doesn't have to exit perpendicular to the surface. Inclined fractures, tubes, and caves can collimate the gas like a nozzle, rotating its vector relative to the local normal. If these mouths are at high latitudes and the spin axis keeps the zone illuminated in a skewed way, the daily average thrust doesn't fall in the orbital plane. Observable clues: narrow, persistent jets with small angular drifts night to night and asymmetric Doppler profiles, blue or red dominance, for several hours. Seasonality with high obliquity. An axis tilted relative to the sun creates marked seasons. One hemisphere is toasted for weeks. If the active sources live there, the net thrust inherits that tilted geometry. The A3 holds as long as the season lasts and decays when the sun shifts hemispheres. Key signal: slow evolution of the thrust vector over days to weeks, not chaotic. Thermomechanical lags in porous material. On fluffy surfaces, heat penetrates and returns out of sync. Gas can percolate through preferred routes and emerge hours after peak illumination, displacing the effective thrust direction out of the plane. A stable thermal lag, visible versus infrared, and a correlation between phase angle and centroid migration are expected. Low amplitude non-principal axis rotation, tumbling. Slight complex rotation can coherently tilt the average orientation of the sources relative to the plane. Here, A3 isn't a fluke, it's composite geometry. It's betrayed by two periods in the light curve and a slow sweep of jet angles consistent with a small precession cone. Multiple out-of-phase jets that don't cancel. 3 or 4 sources with different phases can sum to a net vector out of the plane if the topography and albedo favor those at high latitude. Signature, quasi-periodic modulation of A3, rotation, and short episodes in A4 that don't change the sign of the normal thrust. Residual centroid bias from dust near the nucleus. Even after corrections, a dust gradient very close in can pull the apparent center perpendicular to the plane of motion. Antidote: astrometry in red filters, fewer lines, stable PSF, and polarimetry to separate continuum from emission. What almost certainly doesn't explain the nucleus's A3, solar radiation pressure and electromagnetic forces. They shape the coma and tails, but their direct effect on the massive nucleus is negligible at these scales. They confuse morphology. They don't accelerate the main body. How do we discriminate between these options on December 15th? With coherences. A. A3 stable, following seasonality, obliquity. B. A3 oscillating with 2 periods, tumbling. C. A3 linked to peaks in CnCO2 and narrow jets, oblique nozzle. D. A3 that vanishes when measuring in red bands and after deconvolution, centroid bias. If more tests point to the same mechanism, the anomaly stops being a mystery and becomes a physical diagnosis. And if A3 still persists without a clear owner, one definitive experiment will remain to attempt, predicting its phase and nailing it to the minute on a critical night. Will we dare to play that card? If a small, persistent A3 still has no owner, the most honest and hardest experiment remains. Predict its phase in advance, freeze the parameters, and go observe at the appointed hour. It's the astronomical equivalent of saying, if my explanation is correct, the normal thrust will be maximum at 0217 UTC with a positive sign and will fall by half in 40 minutes. No opportunistic post-processing or last-minute adjustments. You either hit it or you learn. The protocol starts several days before. A working model. Topography with an oblique nozzle, multi-jets, low-amplitude tumbling, etc. is fixed and pre-registered. Rotation period, axis orientation, thermal GR law, minimal map and its phase relative to a timestamp. With this, the orbit is integrated and the out-of-sample prediction is calculated. A temporal profile of the expected normal term, A3T, and its observable correlate in the sky plane. Cross-track residuals that should change. Sign or peak within minute-long windows. Then, an observation window centered on the predicted maximum is designed. High-cadence astrometry, short exposures, 5 to 10 min blocks, filters to minimize lines and DCR, and if AO is available, series alternating deep imaging for jet morphology with clean astrometry. In parallel, a station at a very different longitude repeats the plan so the rotation cycle is sampled in 2 separate phases. If the mechanism is tumbling, the prediction will include 2 peaks separated by the precession. If it's an oblique nozzle, the peak will be narrow and coincide with asymmetries in the jet. The golden rule: no readjustments. The ephemerides and expected pattern are published, even if just internally, the night before, with decision thresholds. We will consider the prediction confirmed if the cross-track peak exceeds 3 Cs, maintains sign, and falls within the plus 15 min window. If it's 2 to 3s, it's classified as a hint, 2 Cs, no confirmation. The same document defines negative controls. For example, checking that the same signal doesn't appear in nearby fields, a systematic, or disappear when changing the PSF or centroid method. What can happen? 3 outcomes with a clear reading. Phase nailed. The peak occurs where and when stated. AO, or space, sees the jet in the predicted orientation. The mechanism gains diagnostic weight, and A3 stops being a mystery. Displaced peak. It arrives with a significant delay or advance. The model needs different thermal inertia, or the active source wasn't where we thought. It's refined, not discarded. 3. No peak. The signal was a composite of biases or non-coherent sources. The A3, if it exists, is below the sensitivity. This kind of crucial experiment yields even when it fails. It reduces the solution space and clears suspects. And if it succeeds, it changes the league of the post-December 15th forecast. An A3 with a known phase allows extrapolating when and how much it will keep pushing. The board is set for a sober decision. With what was measured, without frills, which physical narrative withstands all the tests, and which one falls at the first numerical challenge. We've reached the point where excitement is a hindrance and discipline commands. December 15th doesn't decide with adjectives. It decides with a decision tree that avoids self-deception. If A happens, we do B. If not, C. The important thing is that each branch connects data with physics and, above all, with verifiable prediction. This is how that tree is read. Branch 1. Coherent, thrust within the plane. A2 dominant. A1 small, A3 0. Signals, sustained along track residuals at 3S, repeated at 2 or more stations. Agreement with Q-gas and AFR, stable thermal lag. Reading, standard well-resolved cometary dynamics. Action, fix GR with the gas series, freeze A1, A2, and recalculate the asymptotic vector with narrow error bars. Implication, predictable ephemerides. Subsequent campaigns focus on squeezing light curve and thermal data for size and inertia. Branch 2. Thrust with a small but real normal component. A3 stable 0. Signals, coherent cross-track residuals in phase and sign. AO space Doppler profile with blue-red asymmetry according to phase. Reading, geometry, oblique nozzle, seasonality, or low amplitude tumbling. Action, lock in a minimal model, 1 or 2 sources at high latitudes, and predict the A3 phase for 1 or 2 rotations. If it nails it, the mechanism is upgraded to a diagnostic. Implication, good ephemerides but with a slightly wider vertical inclination band. Follow-up polarimetry and radio to keep dust bias in check. Branch 3. Erratic or multi-source, A2, A3 variable, short peaks. Signals, jumpy photometry. Residuals changing direction in hours. AFER with transient peaks. New morphologies in the coma. Possible co-orbital condensations. Reading, episodic activity and/or fine fragmentation. Action, move from smooth parameters to a multi-jet model with activations by thermal threshold and, if AO allows, track individual fragments. Implication, more fragile ephemerides. More frequent astrometry is required to re-anchor. Priority to occultations and thermal data to not lose control of the effective size. Branch 4. No physical signal, everything 2S, no coherence between stations. Signals, residuals compatible with noise. Discrepancies that vanish when changing PSF, filter, or catalog. Reading, systematics dominated or the thrust is very weak. Action, set upper limits to A1, A3 and report no detection of measurable thrust in this window. Implication, certainty about the asymptotic vector improves due to the absence of thrust. The mass floor is nailed down from the non-gravitational acceleration ceiling. The closing criterion is unique. Out-of-sample prediction. The model that wins today is the one that predicts tomorrow correctly without touching knobs. That's why, at the end of the night, we don't just look for the figure with residuals. We look for the trident that ties the story together. 1. Coherent OC. 2. Light curve with explained phase. 3. Thermal data with correct lag. If all three intersect at the same clock, we have a clean provisional verdict. One figure will then remain for the technical headline and one question for our minds. By how many arc minutes did we shift the real exit path? And what exact window does that open for squeezing the last useful measurements before it's gone forever? With the provisional verdict in hand, the final window opens. A few weeks in which 3i Atlas is still measurable with sufficient quality to round out size, inertia, thrusts, and exit direction. It's not a victory lap. It's closure engineering. It's decided by prioritization. Which measurement brings the most new information per telescope minute? First, the long-tail strategy. As the object recedes, the coma thins and brightness falls. This forces longer exposures, but not blindly. Deep photometry and a couple of stable filters is scheduled to track AFIR and detect residual activity episodes. If the winning model implies a small A3 with a known phase, short blocks at the critical rotation moments suffice to confirm the pattern persists. If it doesn't appear, it's noted as seasonal shutdown, and that branch is closed. Second, precision thermal. At increasing distances, mid-IR becomes costly. So two bands that maximize sensitivity to thermal inertia are prioritized, synchronized with visible to measure lags even when the signal-to-noise ratio drops. One last well-calibrated point can decide between fluffy surfaces, which feeds back into the minimum mass calculation when measurable thrust is no longer sufficient. Third, controlled descent radio sub-MM campaigns. Even as the lines weaken, a sparse series, a few well-timed detections, fixes the slope of Q on the way out and verifies that the GR function used in the dynamics wasn't too optimistic. An error here inflates clones and dirties ephemerides. A couple of honest points corrected. Fourth, unbiased anchor astrometry. Even if the object is faint, a few positions with well-characterized errors weigh more than dozens of mediocre ones. Homogeneous catalogs, red filters, and, if the field allows, lucky imaging are used for better centering. This anchor spills precision over the entire post-December arc. Fifth, archive and reproducibility. The legacy isn't just the nice curve. It's versioned pipelines, complete metadata, catalog, PSF, DCR, times, and codes to reproduce residuals, MCMC, out-of-sample predictions. Publishing posteriors and covariances means that when the next interstellar visitor arrives, the community can start from minute 1 with what was learned here. Sixth, enduring protocols. The 3i Atlas case is distilled into a manual. How to design coordinated campaigns. When to activate crucial phase trials. How to communicate uncertainty without noise. And what minimums of open data guarantee independent verification. This manual isn't bureaucracy. It's the difference between repeating errors or raising the standard. One final act remains. To turn this final window into closing numbers, exit vector, minimum mass, inertia, limits on A1, A3, and into a clear story that anyone can follow without getting lost. Because what we say at the end won't be an adjective. It will be an honest balance of what we do know and what, by its nature, will remain in silence when 3i Atlas is just a trail in the darkness. Conclusion. On December 15th, there were no fireworks in the sky. Yet, for those watching with a cool head, something did change. Our margin of doubt. With coordinated astrometry, clean light curves, synchronized spectra, and well-calibrated thermal data, 3i Atlas stopped being a geometric rumor and became a story with numbers. In that story, science didn't promise miracles. It promised to measure, to decide between hypotheses with evidence and to say with transparency what remained within and what fell outside the reach of this window. If the along-track residuals behaved as a normal A2 dictates, we nailed the sober part of the verdict. 3I Atlas's trajectory is that of a hyperbolic visitor with small cometary thrusts, coherent with its activity. The exit direction was better defined, and with it, the possibility of squeezing the last photons in the following weeks. If a modest A3 also emerged, consistent with the geometry of sources at high latitudes, we frame it where it belongs. A natural mechanism, oblique nozzle, seasonality, or slightly complex rotation, not a mystery. If no signal appeared above 2s, that also counts. We set upper limits on the non-gravitational thrusts, reinforced a reasonable mass floor, and concluded that in this window there was no unusual dynamics. The essential thing is that the method worked. The out-of-sample prediction, that honest game of freezing parameters and going out to observe, set the tone. When the model was right, we gained confidence. When it slipped, we learned where physics was lacking. Different thermal inertia, out-of-phase sources, fine fragmentation, or simple centroid bias that deconvolution corrected. There was no trick, just cross-consistency between OC, photometry, GR extracted from gas, and thermal lags. That convergence, or its absence, is the real legacy. What didn't change? That 3I Atlas is not a danger to Earth. That variations of tenths of an arcsecond speak of diagnosis, not risk. That, at its distance, the value lies in what its chemistry and thrust tell us about material that didn't form here. That our legitimate ignorance, the nucleus's interior, its finest architecture, remains beyond the reach of our telescopes. And yet, with better limits on A1, A3, with light curves fixing periods, and with thermal data framing inertia and albedo, the picture is sharper. In the end, this documentary didn't ask for your faith. It invited you to watch, to measure, to understand why a night without spectacle can decide how an interstellar object will depart, when it's best to observe it for the last time, and what we will learn the next time the sky gives us another visitor. Because more will come, and if something changed today, it's that next time we will arrive prepared. With a protocol, with campaigns that ignite in minutes, with open data anyone can verify, and with one lesson that holds for everything. When nothing seems to happen, sometimes that's when the most is happening.